Awesome. So I'm presenting some work today from my PhD on maximum entropy inverse reinforcement learning. It's going to be a very high level overview of a paper that's coming out next month. So the goal with my research is trying to understand intelligent behavior in the world around us. So we might want to understand behavior for understanding's sake in sciences, or replicate behavior in like robotics or AI development, for example. And the paradigm that I look at in my research is inverse reinforcement learning. So I like to define this as the science, and there's a little bit of art in there as well, but the art and science of rationalizing demonstrated sequential decision-making behavior. So to give you something to grapple on to, or hold on to help this make sense a little bit, you can think of, like, most of you would probably be familiar with logistic regression or something like that, where you're learning a model that fits some data, but those sorts of regression problems, or those sort of learning problems, happen at a single time set. You've got some data, you fit the model, and that's it. This is sort of a generalization of that to a sequential context. We've now got an agent that's making decisions and demonstrating data over time. And we're interested in learning a model of that behavior over time. And that's sort of how this differs from some other types of regression models. I'm not going to go into detail about the math, but we use the Markup decision process as the framework for this. And so you have states, actions, a reward function, transitions, all this sort of stuff. And we talk about policies, which is like how you will act in the MDP, is denoted by pi. And the tricky part here is, in IRL, we're given this MDP, but we don't know what the reward function is. And instead, we're given a bunch of demonstration data, and we want to try and find parameters that make these demonstrations look good. If you imagine we had an expert who plays golf or something like that, and we record them with some motion capture or some cameras or something like that, playing golf at an expert level, we then want to recover these reward parameters that explain their behavior and make their behavior look optimal, so that we can then use those parameters for understanding their behavior, or analyzing their behavior, or recreating it on a robot, maybe. That's an example for you. And like many inverse problems, this is really challenging. There's no unique solution. You have this many-to-many mapping between possible solutions and reward functions to get you there. And so we need additional structure. And a very popular approach is based on the principle of maximum entropy, which sort of says, pick a solution that will make the expert good, but that's not enough. Like I said, it's a many-to-many mapping. So beyond that, maximize the entropy of your distribution. So this is sort of, we're trying to make as few assumptions as possible about the expert's behavior by maximizing entropy of this distribution. And the application that I look at in my work is driver forecasting. So this is a data set available online. It's a year's worth of taxi data from Porto in Portugal. And we can take this data, discretize the road network, and then learn a model that describes sort of the preferences of taxi drivers or their customers. I won't go into the results in detail, but our model works well. We improve over some previous algorithms. And I wanted to show just one cool demo of what you can do with these sorts of models. So we can do goal inference given a partial path. So in this picture here, you can see blue dots. This is like a partial path from a taxi. So the model has observed these blue dots going around this roundabout. Then we're asking it to do inference. Given this partial path, where does the model think the destination is? And these dots, the darker they are, indicates more probability mass. And so you can see it sort of saying, well, maybe they're coming down this street over here, or maybe they're going up to these northern suburbs, and it's actually got one dot where the true destination is. But if we feed the model just a few more data points now, the probability mass has shifted north, and we've actually got this inference that now says the driver is most likely heading north, which is really cool, because the model has learned it's really unlikely for a driver to do a full lap of this roundabout and come back around to these southern suburbs. And so it's learned road rules, it's learned sort of a little bit about driver preferences, and it's still got some probability mass where the true destination is. The code's available on GitHub. It's open source. That's to recreate one of my experiments. It's about 2 lines of code. Thanks to my supervisors for helping me out with this. And if you want to discuss it more, open for some questions, or you can connect with me on Twitter. Thanks, everyone.